Good afternoon, everybody, or good morning, wherever you may be. We will get started here in a couple of minutes as people continue to log in. So stand by, and we'll get started soon. Okay, looks like most people have logged in by now. So welcome everybody to our continuing series called Ask the Moldflow Experts. Today's topic is appearance issues in Moldflow. My name's Tim Lankish. I'm the Director of Engineering here at CAE Services. And I think this is going to be a topic of great interest to a lot of you. I suspect the reason you're attending is that you've had some issues with appearance on your plastic parts in the past. So we're going to talk about how we address such things in Moldflow. This is a little bit about me. Probably a lot of you have attended my webinars before, but if you don't know me, that's my background, physics and math, and I've been here for 28 years at CAE Services. I am expert certified. I've trained 15 plus expert certified engineers. I've contributed to many trade magazines, articles and such, and I've presented several times at the yearly Moldflow Summit. So I've been around the block a little bit with Moldflow and have some pretty extensive background. Our company, CAE Services, was established back in 1988. We have the most expert certified Moldflow engineers in the world here. We are an Autodesk partner, and we've completed at last count some 28,000 plus projects. That's our tech center. So all of our Moldflow engineers have expertise on the molding machines themselves as well. So here's the big question, right? Are appearance issues a big deal? Well, you betcha, right? You know, how much time and effort has been spent over the years trying to correct these types of problems? And I'd say besides warpage, appearance issues are the most common complaint about injection molding. And this is one of those things that can be difficult to correct after the mold is built. And you're going to see as we go through here, you know, why Moldflow is so important is to try to avoid these problems in the first place. You know, time and money is wasted. That can add up quickly. You know, you have engineering time, and maybe even more importantly, you can sometimes weaken the supplier-customer relationships. You know, I've been in meetings, pretty big meetings before with major car manufacturers, where you know, even a knit line can shut down things pretty badly and cause a lot of problems, really. You know, timing issues and so forth, and a lot of finger pointing goes on and so forth, and really it's, you know, all hands on deck once these types of problems shut down a production line. So I don't think I have to tell all of you how big of a problem this can be. So again, the best solution is to avoid the problem in the first place. It's more costly the later the mistake occurs. You know, timelines are extended. and then just the money spent on tryouts, for materials and engineering time and so forth. So we want to try to avoid these where we can. And then there's just the frustration, you don't know what the problem is necessarily, so you try out, and you still may not be able to fix the problem. So we're going to try to avoid things where we can with Moldflow. And one of the big reasons behind that is that oftentimes it's a part design solution that can't be made once the mold's built. How many signatures does it take to go back and get a part design change approved once the mold's built and the production starts up? So we want to try to use Moldflow early on so that we can, if the solution is a part design change, that we can suggest that early enough where we can get that approved. So what are some of the most common issues? And this is not a comprehensive list. These are some of the most common ones. So knit lines and flow lines, of course, are probably the main one. Air traps and voids would be another one. Sink marks is a big one, and gate flush. Those are the four issues that I'm going to address today. Let's start with knit lines. Knit lines are ugly, knit lines are weak, and we want to try to avoid them where we can. It's a blemish that occurs from the collision of two flow fronts coming together. It can reduce the strength. It can be unsightly, and it's often unavoidable due to the geometry features like the one you see here. You have a hole in the part. Flow fronts have to go around them, and they're going to meet somewhere. So it's unavoidable. This also occurs oftentimes on tall standing cores where maybe you gated at the bottom of the core. It flows around the core and then meets on the other side. So this tall standing cores can be a big issue too. So, you are going to be presented with cases where you have an existing tool and maybe you can fix it, but oftentimes you can't. This is an example. This is a riding mower that has a big compartment to the side of the driver here. And when they started molding parts, they saw this giant knit line that was very unsightly. And they came to us to try to see if we could fix that somehow. Of course, our hands are somewhat tied by the fact that the mold's already built. And in some cases, you can get away with molding the part with the hole filled and then maybe punch or machine the hole later. But this was such a big hole that wasn't really an option. So we had to see what we could do to place the knit line in an acceptable area. So can we move the gate? In this case, that was not an option. It had a manifold system in it and couldn't move the drops, couldn't move the gates. Sometimes you'll get lucky where you have a cold gate and you can possibly move it, but typically that's not the case. If you have a multiple gate scenario, maybe you can resequence the flow, maybe not. If you have valve gates, then that's a possibility, but that's not always going to be the case, of course, again. Or maybe modify the part design, and that is the route we chose in this case here. So we used flow leaders and flow restrictors. So here's a look at the before. Showed you the picture on the previous slide, but here's the Moldflow analysis to correlate with that, and you can see right over here that knit line forms exactly as it's shown in the picture above it. So this was good confirmation that our Moldflow model was solid, and that we could start playing what if to see what we could do to mitigate the problem. Looking at the part design, we see you have nominal wall thickness pretty much throughout. Some areas are thinner, but by and large, the shell of the part is all one thickness, around 3 millimeters. And we started playing around with different wall thicknesses. We went thinner on the green area here and thicker in the orange area there. And by doing so, through simulation, we see that the knit line is able to form over off to the side in a much more desirable location. And so they accepted that. We made the changes to the tool, and you can see the knit line falls exactly where a Moldflow is showing that it can. great, we were able to fix that one. This isn't always going to be the case. It's not always going to be the case that you're able to make the part design changes you want to make this happen. Processing changes are often difficult as well when it comes to knit lines. It's very rare that process changes can move knit lines much at all unless you're getting into valve gate sequencing. So that's fixing knit lines in an existing tool. What about avoiding them altogether? So if I threw this part in front of every one of you here, and which there are 99 people online right now, I bet I'd get about 99 different answers. How many gates would you use? Where would you put them? And this is where we start asking questions, right? Where are the knit lines acceptable? So we have to talk to the customer about that. Where are the gates acceptable? In this case, we weren't allowed to gate on the outer flange of this part. They had to be all direct gates. Can we use valve gate sequencing? In this case, that was acceptable. So we looked at that. Can we modify the part design? That's always a big question before we get into a program as well. It's amazing to me how many times the answer is no right off the bat, but when we start playing around with different part designs and showing them what's possible, how quickly we are able to change minds in those cases. So don't necessarily take no for an answer from the get-go. Keep plugging away with different part design options to possibly convince your customer to go that route. So, if I didn't ask any of those questions, maybe I would have just gone right ahead and tried to balance the gating, just started throwing gates on there and throwing, just pick 8 gates, 4 on the left, 4 on the right, and run them all open. And maybe I got those knit lines right there in the middle of that, and we got on a go-to meeting, and my customer said, well, that's great, pressure's low, everything processes well, we can make this part no problem. Maybe even the warpage is good, who knows? But now we got these knit lines right in the middle of an appearance area. So that's one of the reasons we want to ask those questions, and one of those reasons we want to be able to do this ahead of time so we catch these type of problems before they occur. That's a map pocket area right there. You can't have visible knit lines in that area. So after iteration after iteration after iteration, and I think on this particular project we went through some 20 to 30 iterations, we came up with this. So all direct gates, as you can see, we start with this gate on the bottom, let the flow get through the map pocket without any knit lines, and then we start boosting it from there. So we're able to sequence from the bottom to the top and avoid the knit lines in that bottom area there. Here's another situation where we were able to avoid knit lines. This old Dodge Viper here, pretty cool part. And on the left here, we see a couple of ideas that were proposed early on with the original part design, drop locations and the valve gate sequencing from the center out. And you can see some of the flow coming back and forming knit lines in very visible areas here. You can see these red lines here would be very visible knit lines. So after suggesting some part design changes, thinning the walls out on the bottom, for example, and moving some gates around, adding some gates and so forth, we were able to push knit lines out to the extremity here. So we still were left with one little knit line here that we couldn't get rid of. We proposed thickening that center bar there. They did not want to go with anything thicker. But they were okay with that knit line being there. So, there's millions of permutations and combinations of wall thicknesses and gate locations and so forth that you can play around with, but the key is to do it up front. If you're stuck with a situation where you have, say, this kind of a manifold system in your tool and the tool's already built, there's not a whole lot you can do after the fact to mitigate these knit lines. So really important to identify this problem before it happens, and then play around with a lot of different solutions, potential solutions to fix the problem before the mold's built. Another issue we come up with is the predictions themselves sometimes can fool you. So, if you haven't done a lot of Moldflow work, you could get yourself in a situation where it may not pick it up if you haven't meshed the part densely enough. Here's a situation right here where a knit line formed in the corner. They had actually done their own Moldflow work on it, and they did a full 3D model, 1,000,000 elements, thought 1,000,000 elements was a lot, wasn't able to pick up that knit line. And then when it got remeshed with 3.3 million elements, when we got our hands on it, that it picked up that knit line right there. And we were fortunate in this case that we were able to play around with some wall thickness changes, and we were able to add a gate in a certain section of the part to be able to move that knit line out of that area. But again, that's not always going to be the case. So the crazy cousin of the knit lines are flow lines. These happen in molds where we have a valve gate sequence situation, multiple gates. And it's a blemish that occurs from the acceleration of those flow fronts. So what happens is we have valve pins in pressurized nozzles opening quickly. So maybe we gate something and we fire one nozzle, let the flow go a certain distance, and then we fire the next tier of nozzles, and then so forth and so on. And what happens is we see these either hesitation marks or acceleration marks you see on the left here, and that can present what looks like a knit line, but it's really a flow line, as we call them. So several manifold suppliers have come up with the idea of using a valve gate control, velocity controlled valve gate retraction. So rather than these pressurized nozzles having valves that open almost instantaneously, they retract them slowly to be able to avoid this hesitation and acceleration type phenomenon. And you can see the before and afters here are pretty remarkable. And here's how it looks in Moldflow. So in Moldflow, we have the ability to time our valve gates however we want, either by flow front action, trigger, time. We can do it by position on the machine, screw position on the machine, lots of different ways to trigger valve gates in Moldflow. And now we have the ability to retract those pins slowly and control the velocity of the valves as they open. So you can see the difference here, and you see these hesitations here as each successive set of nozzles opens. We get the hesitation, then we get this acceleration, then a hesitation, then an acceleration. When we change that to velocity controlled valve pin retraction, you see a much smoother progression of the flow across the part there. So that's what we're aiming to do, and we can play around with different variables there, different gate locations and so forth. So again, you get into a production environment, you're going to be a bit handcuffed. Number one, if you don't have valve gates. Number two, if you don't have velocity controlled valve pins. So just way better to do this up front than after the fact. Next on the list is air traps. Air traps are formed because air that occupies the mold that should get out as the plastic flows doesn't. It's supposed to be able to vent the air through vents. Sometimes those vents come from maybe ejector pins and so forth, but typically it's going to be on the parting line of the mold. So if the formation of those air traps doesn't occur in a ventable location, then these air traps can form. So the part design, gate position can produce these backfilling or racetracking effects. They can cause non-fills, or they could possibly actually burn the material. That burned material comes from compressed air. That that volume of air gets compressed as the backfilling occurs. And as we know from our old chemistry books, compressed air leads to higher temperatures of the air. So that's what happens. And if it's high enough to burn the material, then you might see a burn mark on your part. In the case of short shots, it's the compressed air pushing back the buildup of pressure in that area, pushing back on the melt enough to keep it from filling. So here's a case of an air trap in an existing mold. This is a part design issue. This is a medical part with a cannula in the middle. So part design change wasn't much of an option here. This is how it had to be designed, but we have thick and thin sections kind of playing against each other. You know, it wants to fill the thick sections, and it fills them very easily, but meantime, some of the material gets into these thin sections and starts hesitating. And so you see once the thicker sections fill out, now it starts to dedicate some of its flow back to the cannula area and then fills out. But by then it's too late. We have an air trap there. So mold was already built. We came up with the idea of filling a little bit faster. Surprised they didn't come up with that themselves at the mold tryout, but that is one way to fix the problem, is to fill faster to reduce the sensitivity of this mold to those fill speeds, to the thickness differences, I should say. You know, keeps the material warmer longer so that it doesn't hesitate quite as much in the cannula, and allows it to fill out. Now there's still kind of a nasty knit line there. That V shape that's forming is going to form a bit of a knit line and might weaken that material there. So the real solution to this would be to thicken that cannula a bit if we can, or conversely, thin the other areas out. But this is one of those situations where they were not willing to change part design. One of the ways to fix things is through a vacuum venting system. This is an aside from Moldflow, but this is a product we sell called the Mold Vac. So before and after, you can see, you know, if you're absolutely stuck and you've built the mold and you know, you have this backfilling kind of condition, you can fit the mold for these mold vacs and pull a vacuum on it to get the air out of there so that it doesn't compress and superheat and cause short shots and so forth, or burns. So that's one way to do it. You know, again, you want to try to avoid all this situation as much as you possibly can. So this was another case for an existing tool. We had a part design change in this case. This air trap in the optical area was unacceptable. You see some short shot pictures here forming right to left, actually. So this area in the center of the part was an optical area. There's some kind of a viewing type of a device. So that was unacceptable. It wasn't causing a short, but it was, you know, causing a knit line in there which screwed with the optics. So we increased the wall thickness in that optical area as much as they would allow it. And by doing so, you can see we were able to push this knit line / air trap off to the side out of that center viewing area. So ideally, we would have come up with something that pushed it all the way off. But again, you know, you're in a situation where the mold's already built and there's only so much you can do. So the air trap was moved to an acceptable area. Here's another case, often overlooked, but equally as important: core shift. We see this, you know, more frequently than you might imagine. So we get a pressure differential caused by the flow of the material on one side of the part well before the other side of that core, causing a pressure differential between the two. And if the core is, you know, typically tall and somewhat thin, or somewhat unsupported, it can shift it to one side and cause thin area on the side opposite the gate and a thick area on the same side as the gate. And that's what we had in this case. So they had a gate on the top of this core, kind of off to the corner here, and caused that very condition. So you can see the blemish that occurred here on both the outside and the inside of this part. So that thickness change causes backfilling, and that led to a blemish. So, you know, just in standard Moldflow on the left here, no core shift being done. You see the slow progression here, and you know, if you didn't think of core shift, you would not have picked this up. You see the gate over here in the corner, and that's causing a pressure differential across the core. That Moldflow is picking the pressure differential up, but it's not picking the core shift up because we didn't run it that way. So, you know, this is kind of a false positive in Moldflow, and this is where you got to be thinking about it. Well, when we went back and we actually measured some parts in this case because we knew we were going to start playing around with wall thicknesses, and we built a mid-plane model to be able to do so. So we modified the wall thicknesses on this to mimic what they were seeing in reality. And sure enough, we're seeing this backfilling condition here. So they were planning on building a new tool to mitigate this expensive fix, to be sure. So in doing so, we recommended they move the gate over to the side. And we actually ran a core shift analysis on this, full 3D analysis, and you can see in this case, we got very even flow on both sides of this core and eliminated that core shift. So again, going back to the issue of let's fix it all before it happens, we have a lot more at our disposal. Here's just another case, kind of like that viewing optical piece. We played around with a couple different, gating scenarios. In this case, they really wanted to go with a subgate so that they could have the automatic degating, and not have to deal with a hot runner system. So we worked with that initially and noticed that there was going to be 2 air traps in this case, one over here on the right wall and another one right at the top of this center core here. Move the gate a little bit around. We're able to get rid of one of those air traps, but no matter what we did with a subgate, we were going to end up with an air trap at the top of this core. So, the final decision was, okay, well, let's simulate just gating right on the top of that core. Didn't really want to have to do that, but in the interest of saving all the headaches of having this air trap, having to deal with this air trap, they decided to go ahead with that center drop there. Here's a case where a design change and a gate change made the difference for a new generation part. You can see there's a little bit slight difference in the 2 parts. Initially, all these big rectangular standing cores they were going to keep them in the center like they did in this case. But because we had an air trap problem there, and even if we reduced it to 1 gate like we did over here, we still would have had that air trap. So we decided to move that over and shift these 4 standing cores to the opposite side of that. And that made all the difference. We knew we were going to get air traps on the tops of all these cores because they're tall standing cores. But we wanted to try to avoid as many of them as we could by modifying the part design. So this is one of those issues where, we were able to play around a little bit with the part design and the gate design before production started, and we're able to get a much better situation to deal with. Here's a case with a thin membrane in the middle of the part here. Very thin membrane, 0.2 millimeters. So, at risk of actually shorting this particular part, keep in mind that Moldflow assumes air is going to get out wherever it needs to. So in Moldflow, it's predicting that it's going to fill here, but in reality, you could potentially see a short shot. So again, this was a situation where they were building new mold and they wanted to figure out a way to mitigate this. So we came up with the idea of using an injection compression solution. So what that means is that we had this core retracted a little bit, and we played around with different retraction distances to essentially allow the flow to get across the membrane and then coin it, squish it, compress it to get it back to the 0.2 millimeters. So here's what the flow front looked at when our start position was at 0.6 millimeters. So still looking at a little bit of backfilling. And then we ended up with 1.2 millimeters to get a nice even flow across that membrane. That membrane was very important, very functional piece in this medical part. So if you watch this animation, you'll see this core start to move. And that's something we were able to play around with in Moldflow, the speeds and the retraction distances and all that. So once the material got through there, we started the coining process, and we're able to get that down to the 0.2 membrane thickness that we wanted. Total time on that was 0.6 seconds. So we had to fill it fast and we had to squish it fast. Next on the list here is sink marks. This is a big topic for discussion. So Kind of hard to see there, but we have a little bit of a kind of a U-shaped feature on the back side of this part that's reading through. And over here, we have actually a corner sink mark where uniform wall stock was not maintained going around that 90-degree wall there. So this is a big one. It's a depression at the surface where the backside features intersect. Sometimes happens in very thick sections where there's not kind of an intersection on the backside. This is caused by excessive shrinkage. That's essentially what a sink mark is. Usually in thicker sections, farther from the gate, forming at higher temperatures perhaps, so cooling can play a role in that as well. Higher shrink materials, of course, are more susceptible to this phenomenon as well. And then, like I said here, beware of the corners. So if you have a situation, where you've got a corner going like that, or maybe you square it off a bit, and then you try to have a big sweeping radius on the inside, you've got a lot more material there to deal with. So that can cause a big problem. So you want to make sure in your corners that you have uniform wall stock wherever possible, or else you make yourself open to sink marks. So on an existing tool, improving sink, you're kind of at the mercy of the design at this point. But you definitely want to check your processing. Do a gate freeze study, number one. Run a bunch of different pack times and make sure that you don't see this kind of a situation. So if you trim all the gates and you measure the part weight, you don't want to see the weight reduce as time goes on. Basically, you want to make sure that weight stays constant. Once that weight starts to stay constant over time, no more material can get through the gate. So presumably the gate is frozen and you've exhausted as much pack time as you possibly can. Because what happens in this situation here is material starts to leak back in through the gate. So you're not taking full advantage of what the gate is giving you to pack out the part. So make sure you're doing a gate freeze study. Again, there's not much you have at your disposal, but I've seen it happen where you go back and try to reduce the rib to wall ratio. So, major tool modifications generally need to be made in those situations. Maybe some welding, so forth, to make that happen. That is not a pleasant experience to have to go back and do that after the fact. Increasing pack pressure, that's another process fix. Problem with that is now we're making ourselves more susceptible to the clamp force requirement. Moving gates, this may or may not be possible, and it could cause unintended consequences. So if you're not sure, what you're doing there, let's say you have a glass fiber filled material, for example, you start moving gates around. Now your fiber orientation changes and may completely change the warpage pattern of your part. So be careful with the moving gate solution. But if you do decide to do that, make sure you move your gates closer to those areas that require, or those areas that are seeing the higher sink. So if it's a new tool, obviously you want to try to use the simulation results. Best solution is to reduce the rib to wall ratio. Obviously no welding involved because we haven't made the tool yet. A lot of folks like to use sink savers where they thin out the area closest to the intersection with the main wall. Or sometimes they'll thin out the whole rib or the whole boss or whatever it may be. But you got to be careful with that because you got to be aware of short shots. Here's a situation on the right here where I've got 3 different scenarios where we've got the 4mm wall, the base wall with a 2.7mm boss. With thinner and thinner walls being manufactured these days, you got to be really careful with this. So you see these numbers going up as we go from left to right here when we have a larger rib to wall ratio. Again, moving gates closer to the areas of sink is important where we can. And I get a lot of questions. What's the number we need to find? What's the number we need to stay below in Moldflow to ensure that we don't have sink mark issues? So the number we try to stay below is 0.1 millimeters, and if there's glossy finishes, we go about a quarter of that. That seems to have worked. I have not seen rigorous studies done on this correlation between mold flow and actual sink mark depth. I believe GM maybe has done a little bit of work on this, but I have not seen the results of that. But in any case, this is one of those things where it's kind of a trial and error type of a deal, and this is what we've worked with in the industry for quite some time, and it seems to have served us well. Next issue is gate blush. You can see a couple of examples of it there. It's a blemish extending from the gate. It's caused by material degradation, where we have excessive shearing, breaking molecular chains. Usually occurs in thin gates, small gates, molds with too few gates, because you have all the material going through one gate, for example, on a large part. Perhaps the fill rate is too fast. All of those things can cause excessive shearing. So what you should know is that each material has a shear limit. And if we look at the diagram here, plastics flow in a laminar fashion. So if we look at the direction of flow left to right, each one of these laminates or layers moves at a different velocity. And it's that change in velocity over the distance, over the vertical distance here, that causes shearing. Okay, so shearing is measured in reciprocal seconds. Kind of a funny name, but if you do the math, it's basically a velocity divided by a distance. So the distance units cancel and you're left with reciprocal seconds. So it's the rate of change of velocity between adjacent layers. So on the outer layers here, you see the most shear, right? Because you get the biggest changes in velocity when you go from one layer to the next. So, you know, distance between the first two layers and the second two layers and all that, that's all the same. That doesn't change as you move through the thickness, but the velocities do change, and you see the biggest delta U's out here in those outer layers. So you typically see the biggest shear out near the skin of the wall. So that's what shear is, and every material has a shear limit. And the Moldflow database publishes numbers, but these limits are not something that are specifically tested for. So if you ever get a material test done for Moldflow usage, know that that's not something that's specifically tested for. So consequently, we keep when we're doing analysis work, we keep that number, try to keep that number significantly below the limit. You know, I target 50% typically. Some people target even 20%. So when we're doing analysis and we're figuring out how many gates and how big the gates should be and where they should be and so forth, this is what we use. We use the shear rate limits as our guide. If you ever wanted to specifically test a material, you could. You could change, you know, fill speeds. You build a test mold, change fill speeds or gate size, and calculate the shear rate going through a given gate, and just note when the onset of gate blush occurs, and you know, match that back to your mold flow predictions. Here's just a quick example of changing gate size. You could slow down the fill speed. Again, that could cause some unintended consequences. It's great through the gate, but maybe elsewhere it's causing problems. It's typically best to increase the gate size. That may or may not be undesirable from an aesthetic standpoint if it's leaving a large gate vestige, or perhaps maybe now you're putting yourself in a situation where you have to trim gates. But you know, that is generally the best way to reduce quickly the amount of shear you're getting through a gate. Larger gates could also cause some sink issues near the gates as well. So you know, again, it's that whole trade-off thing in plastics. You fix one problem and create another. In this case, you know, we have a material limit of 100,000 reciprocal seconds. So this is a polypropylene. You know, and with this tiny little gate that they wanted to use, 361,000. So we're exceeding that by quite a bit, and very likely that we're going to see some type of a blemish in that area. And then, just by going to a rectangular style cashew gate here with a thicker cross section, we're able to reduce that to nearly half of that number. So that's just a quick example of how we do things in Moldflow. So for new tools, again, you use simulation results. You want to ensure the proper number of gates. Again, you get in these situations where you're trying to fill a giant part with one gate, probably not going to work out well for you. So we got to ensure the number of proper number of gates, first of all. Increasing gate size, I already mentioned. Ramp speed profiling is another way to go. If you're in a situation where you might need to use processing to fix your problem, you've increased your gate size as much as you can. You can't add any more gates and so forth. You could possibly just run the material slower as it comes through the gate early on in the flow, and then go back to a more normal fill speed from there. Again, the best solution to all this is avoidance. So make sure your part is feased. We do feasibility studies here at CAE. These feasibility study assures us that the part is good for tooling. It's sufficient sidewall draft, for example. But the big one, for appearance issues and sink marks and so forth, particularly rib to wall ratio. So that's one of those things where you look at a part from a 30,000 foot view, and you don't even have to do Moldflow analysis to catch some of these things. So it's good to do these feasibility studies beforehand to catch some of these issues before they even start. So some parting thoughts here. So use simulation up front before the mold is built. I'll say it time and again. It doesn't matter if it's appearance issues or warpage issues or processing issues or any issue you can think of with plastic injection molding. Do the simulation up front. Don't wait till the last minute, because you're asking for trouble. The 28,000 plus projects that we've done, early on 28 years ago when I started doing this, they were mostly fixer-uppers. Our customers would come to us and they'd have a problem in a mold that's built, and over time the tide has changed. People are doing Moldflow up front to be able to mitigate these problems before they happen, and that's the best way. And a lot of companies are demanding it to be done on all of their molds well in advance, because they know the pain and suffering that occurs when you don't. You're not going to catch a problem on every mold, but or there may not be problems on every mold, but the ones you do catch the problems on more than pay for the ones that don't exist. So use simulation up front. That's a standard. Make it a standard. I'm a big fan of hardwiring solutions into the part of the mold design. If you have to go back and figure out the process that's going to fix all your ills, you're asking for trouble again. Processing window, big processing window is where we want to start, and that starts with good part design and good mold design. So we want to make sure we have all the uniform wall stock and do your part feasibility studies. Make sure you're placing your gates right, make sure you're placing your cooling lines right. All of those things give you a bigger and bigger and bigger molding window to work in. So let's try to hardwire solutions into the part of mold design. And again, the only way to do that is to do this well in advance. Use expert Moldflow engineers. I don't care if it's us or your own. We've got a lot of guys here that know what they're doing. We're an old Autodesk partner as well, so we're training a lot of engineers out there to use Moldflow properly. Their expertise is going to help us know when the results are reasonable, whether or not we've got good material data. Can we trust the results we're getting because we've got good material data? Do we have the right mesh? Are we using the right mesh type? Are we using the right mesh size? You saw that knit line that was missed earlier because the number of elements they put on the Moldflow model was insufficient. The engineers are going to know how to identify the causes by using Moldflow, and how to solve those problems through mold and part design, or if it comes down to it, how to process it. So it's really important to not only use Moldflow, but know how to use Moldflow. So can't stress that enough. So here at CAE Services, I mentioned the feasibility studies, mentioned our Autodesk partnership. We sell the software, we train people in the software, and we mentor people in the software. If you ever want to, we suggest everybody has some level of Moldflow, whether it's the Advisor series or the Insight series. Everybody should have some Moldflow software in their back pocket. For learning, we're building expert analysts. We're doing these webinars. We're training in the classroom and online. We have our webinars in our Moldflow office hours. So if you ever just want to pick a topic and pick my brain for several hours, you can pay to sit down with me and do that. And then, of course, if you need to get in contact with us, go to our website. There's a lot of good information there. Follow us on LinkedIn and so forth. So questions. Some of the questions that were submitted, there was a common theme among a lot of these, but I'll just pull a few out of here. Jetting, there was a question about jetting. Moldflow actually can predict jetting. There's special switches you have to turn on and so forth when you're doing a full 3D analysis to be able to predict that. And there are ways to reduce/eliminate the jetting by how you gate the part and how you do the part design. But again, make sure you're doing this up front on very thick parts when you suspect jetting may occur. Another question about flash. How does Moldflow predict flash? It doesn't specifically predict a flash, but we use the clamp force results to be able to tell whether or not we're running up against the machine's capabilities. So, if for example, we gate it a certain way and we process it a certain way and we see the clamp force prediction, getting within, let's say 10% of the clamp force limit, something to consider. Use a larger machine, or better yet, let's produce a mold design or a part design that's going to get us in a situation where we're not even close to that. So, there's always tooling issues too. Moldflow can't predict when poor tooling is made, causing flash, but we can, from a processing and a mold design and part design standpoint, tell you when you better raise a red flag. Vacuum voids and air bubbles. That was another common question. A lot of that depends on consistency. If you're molding parts and you're seeing air bubbles, but the air bubbles are occurring in a lot of different places, that's probably not an issue with the part design or mold design necessarily. It could be, but oftentimes that's going to be a material drying issue. Could be a part design issue from a standpoint of, thick sections again. Maybe you have a stiffer material and it, instead of sinking, the material freezes on the outer layers, and then, the shrinkage of those thicker areas inside start to shrink towards the frozen material that's already adhered to the mold wall. So in that case, it's generally a part design issue. In those cases, you would probably see those voids a little more consistently in the same spot. But air bubbles that move around, that generally is a material drying issue. In conjunction sometimes with the shearing of the material, heating up things and causing those bubbles. I also get questions about tiger stripes. Can Moldflow predict tiger stripes? Moldflow is working on that. It's not in the commercial code. There's no promise to have it in the commercial code, but I do know they are working on it. So stay tuned on that one. That's typically in TPO materials. And there's some oscillating effects that go on with I believe it's a shear condition that reacts with the rubber component of the TPO. Don't quote me on that. This is going from my memory. But again, not in the Moldflow code at this point. So, and again, not promised to be in the Moldflow code. So that's the status of Tiger Stripe predictions. A lot of questions about what's the right temperature for knit lines. There are a lot of theories out there on knit lines and what causes them to be visible and so forth. Generally speaking, you want to try to keep them, near the temperature that you filled the mold at, the melt temperature, and keep the difference between the two advancing flow fronts that are colliding as close to the same number as you possibly can, say within 10 degrees or so. But again, I'm gonna preach the avoidance thing here. So where you can avoid the formation of knit lines, absolutely do so, or put them in a less conspicuous area. And then also questions about predicting strength, and that is something Moldflow can do. In more recent revisions, the prediction of 3D weld lines is getting better and better, and the ability to transfer that information over to structural analysis programs is available as well. So that that ability, that is not something I specifically have worked on myself, but the capability is there and is getting better. So Matt Jaworski over at Autodesk has done a lot of good work on that. So that's all I have at this point. I hope it was insightful and helpful to you. If you have any questions, feel free to email me or get on our website. There's my email address, or give us a call. Love to talk to you directly. And I'll answer any questions you have. In the meantime, look for our next webinar next year. We won't see you till then, so have a good holiday season, Christmas, Hanukkah, whatever you celebrate. Make it a good one, and have a happy new year. Thanks, everybody.